black magic has picked up. It had applications in all walks of life, and now it has found a new application. It's found an application in education, JEE preparation. Now, how I discovered this was when I was going through videos of so many institutes, so many online platforms, the big guys. That's when I figured out that there is application of black magic in education. Now, there are two variables involved there. There is an independent variable x and there is a dependent variable y. Wonder what this x and y are. Y designates the additional marks that you're going to score. The additional marks that you're going to score marks scored. And what is x? X is the time spent. Time spent doing what? Time spent preparing for 2 years? The number of minutes you have spent in 2 years towards your JEE preparation? No, not at all. X denotes the time in minutes. Time in minutes that you have spent watching the video of an institute ABC. How to score Y marks in X minutes. How to score Y marks in X minutes. Y a function of X. Y a dependent variable, X an independent variable. Now that's the formula. There is a correlation between X and Y, the number of minutes you have spent in those magic videos, and Y the marks scored consequently, additional marks scored consequently. Now that's black magic. What would you call that? Right? In the sense that, when you watch those videos that claim that you can score Y additional marks for every X additional minutes that you have spent in those videos, what they do is they invoke ghosts. Yes, they invoke ghosts. And then when they invoke ghosts, depending on the institutes, different institutes have access to different ghosts. Therefore, Y a function of X is different for different institutes. Somebody will tell you 2 marks in 4 minutes. Somebody will tell you 4 marks in 2 minutes. That changes from institute to institute because their accessibility to ghosts is different. Surely, I'm still trying to learn the trade. I'm trying to see what is happening there. I've still not learned those magic tricks. Abra kadabra, gilly gilly go, ja tera IIT ho. Far from me. As of now, I have not been able to discover all of it. So, surely while I'm still learning black magic and give you the magic potion to clear IIT JEE, I will continue to share with you some mundane revision classes on various topics that could be useful. They're not almighty, but they could be useful, and that would be an add-on to your 2-year preparation for JEE. So, with the commencement of this revision series that I offer to my beloved students, we start with this topic on matrices, which is an important topic, not difficult, it's scoring, and almost every year there are problems that are posed in this topic. What this bunch of problems will do to you is, it will give you a quick brush up of the basic results in matrices, just in case it's been long forgotten. You might just get into the groove of matrices. So this first session of mine, which is a revision session on matrices, surely not as advanced as the magic potion, not as advanced as black magic, voodoo, tantra, witchcraft, very mundane basic stuff, right out of what is prescribed in matrices in terms of results, problem solving, techniques, and so on and so forth. I hope this turns out to be useful. Although, when you start comparing it with the magic pills offered by so many online platforms, you would find it wanting. Unfortunately, I will not be able to offer all of it right now while I'm still trying to learn the trade of magic pills, but I hope this one session on matrices does good to you. Bye-bye. See you with some problem solving. Have fun until then. So we have A and B, two square matrices of order 3, 3 by 3 matrices. And determinant of A is given to be -2, determinant of B is given to be 1. We want to be able to find the determinant of A inverse into adjoint B inverse into adjoint 2A inverse. That's what we want to be able to do, right? So first things first, determinant of the product would be product of the determinants, right? So this is determinant of A inverse into determinant of adjoint of B inverse into determinant of adjoint of 2A inverse, right? And determinant of A into determinant of A inverse is always 1. You know this, right? Because A inverse is I, so determinant of A inverse would be 1. So determinant of A inverse would be 1 by determinant of A, right? Now, adjoint, determinant of the adjoint of a matrix P, determinant of the adjoint of a matrix P, do you realize, did you know, must be knowing, or at least do you remember, must be determinant of P to the power n minus 1, where n is the order of P. P is a n by n matrix, right? So if it's an order 2 matrix, then order 3 matrix, then n is 3, adjoint of P would be determinant of P to power 2 if n is 3. Here we have matrices of order 3, 3 by 3, right? So look at adjoint of B inverse. So determinant of adjoint of P in B inverse would be determinant of B inverse whole square. But determinant of B inverse is 1 by determinant B. So that's going to be 1. Right? Yes or no? So this is 1 by determinant of B whole square, adjoint B inverse, right? Now, adjoint, determinant of adjoint of 2A inverse similarly is going to be determinant of 2A inverse whole square for a 3 by 3 matrix, right? Now, determinant of 2A inverse is what? Right, 2 cube, because, right, every element of A inverse will get multiplied by 2, so the determinant will become 8 times. Yes or no? The determinant will become 8 times. So this is 8 times 8 and then whole squared. So that is 64. Determinant of A inverse whole square and determinant of A inverse whole square. So that is 64 into determinant of A inverse whole squared would be 1 by 4. Yes or no? Because determinant of A inverse would be 1 by determinant A, so 1 by 4 is, so that makes it 16, right? So this is into 16, and 1 by determinant A is -2, so minus 1 by 2 into 16, that makes it -8. -8 is the value. Got me? Do you know what this result is? Determinant of adjoint A is determinant A to power n minus 1 whole square. If you have adjoint coming once, it's going to be square. It's going to be to power n minus 1, and now it's going to become n minus 1 whole square. Right? Stand by. N is second problem of the sheet is about two matrices A, which is this, B, which is this, and it's given that AB is not an identity matrix. Also, it's given that AB is AB inverse. What we want to find is, what we seek to find in this problem is the trace of AB plus AB whole squared plus AB whole cube plus AB to power 100. That's what we want to be able to do, right? So, first things first. Let's find out AB. Let's find out AB in terms of x, right? What's AB? AB, let me multiply the two matrices out. Okay, I have minus 2x plus 0 plus 7x, that makes it 5x. And then I have 2, 0, 7, 28x plus 0, 28x, 0. And then I have 14x minus 14x, which is 0. Okay, let me come to this. 0, 0, 0. All right. Then 0, 0, 1, and 0. All right. 0, 1, and 0, 1. And then 0, 0, 0. All right. And then let me come to this. I have minus x plus x, so that is 0. And then I have 14x minus 2 minus 4x, 14x minus 4, so that is 10x minus 2, 10x minus 2. And then I have this last element, 7x, 0 minus 2x, so 5x. So right. So that's the matrix AB. That's the matrix AB. Good. Now let me look at what's given. AB is AB inverse, which means, can I not say that AB whole squared? Let me multiply both sides by AB. That's going to be equal to AB inverse into AB, right? But AB inverse into AB would be an identity matrix. So that's going to be I, right? So that's AB whole squared. Let me take the determinant of both sides. So which means determinant of AB whole squared would be determinant of I, which is 1. And determinant of AB squared is like determinant of AB whole squared. That's 1, which means determinant of AB can be plus or minus 1, right? Determinant of AB can be plus or minus 1. Now let me go to AB and see what happens when I apply determinant of AB is plus or minus 1. Now what's determinant of AB from here? See, determinant of AB from this matrix, AB is 5x into 5x, 5x whole squared. And then these two will produce 0. And that must be plus or minus 1. That must be plus or minus 1. Very clearly, I'll assume that x is a real number. So 5x square can't be negative. So 5x square must be plus 1. And if 5x square is plus 1, very clearly x can be plus or minus 1 by 5. Right? These are the two possible values of x. Plus or minus 1 by 5. Now, if I take x equal to plus 1 by 5, what happens? So if I took x equal to plus 1 by 5, this will become 1. This is 1. This will be 1. And this will be 1 by 5, 2 minus 2, 0. So it will become an identity matrix. So if I took x equal to plus 1 by 5, AB turns out to be an identity matrix. But it's given that AB is not an identity matrix. So x equal to plus 1 by 5 is ruled out. X therefore must be minus 1 by 5. X therefore must be minus 1 by 5. Given that, what's AB then? AB then is like 1 minus 1 by 5, so minus 1, 0, 0, 0, 1, 0, 0, minus 4, and then 1. That's AB. That's AB, right? That's AB. Now, if that's AB, very clearly, trace of AB is what? Minus 1 plus 1, and of course this should also be minus 1, right? Because x is minus 1 by 5. So what's trace of AB? Trace of AB, as you can see, is minus 1. Trace of AB is minus 1. Sum of the diagonal elements, that's minus 1. Now, what about AB whole squared? What about AB whole squared? Come back to this. See, AB whole squared was essentially an identity matrix. AB whole squared is an identity matrix. So AB trace of AB whole squared. Trace of AB whole squared, as you can see, right, would be 1 plus 1 plus 1, the identity matrix, right? The identity matrix. So that's going to be 3. Trace of AB whole squared. What about trace of AB whole cubed? Now, if AB whole squared is I, then AB whole cubed multiplying by AB throughout would be I into AB. That's AB. That means trace of AB whole cube would be the same as trace of AB. Trace of AB whole cubed is the same as trace of AB. And going this way, we find that trace of AB whole cubed, trace of AB whole to power 5, etc. All of it would be minus 1. That means odd powers of AB will produce a trace which is minus 1. What about even powers of AB? Hey, trace of AB whole squared is 3. Similarly, you will find trace of AB whole to power 4 as also 3. Why? Because realize that AB whole to power 4 would be like AB whole squared, square of this, right? But what is AB whole squared? AB whole squared is I, and square of this will still produce I, and therefore trace of AB whole to power 4 will also be 3. Trace of AB whole to power 6 will also be 3, and so on and so forth. So all even powers of AB will produce an output that will be 3, right? So good. We need to find trace of AB plus trace of AB whole squared, AB whole cubed, AB to power 100, and we have 50 odd powers, 1, 3, etc., and 2, 4, etc., even powers, 50 even powers. So what would this be? The 50 odd powers, AB whole cubed, etc., will produce an output which is minus 1. And there are 50 even powers, AB whole squared, AB whole to power 4, AB whole to power 6, and each of those will produce an output which would be 3, which would be 3. So 50 into 3. So 150 minus 50, that is 100. So the answer to this is 100. The answer to this is 100, right? The next problem, again, not difficult, is about two statements given. M, a 2 by 2 matrix, call it ABCD. M times this matrix is this matrix. M square times this matrix is this matrix. And it's given that determinant of M minus xi, where of course I is an identity matrix, gives me two values of x equal to x1 and then x equal to x2, two roots. x1 larger than x2. Given all of this, we want to be able to find the value of 5x1 plus 2x2. That's what we want to be able to do, right? Now, only for convenience, let me call 1 comma minus 1 as the matrix A, and let me call this as matrix B, and let me call this as matrix C, right? So M times A is B, M times A is B, and M square times A is C. I'm seeking to find M. That means I'm seeking to find A, B, C, D, etc. Right? Now, if M square times A is C, I could have written this as M times MA as C, right? But what's MA? MA is B, so that gives me MB, MA written as B, MB equal to C, right? Now let me take these two equations, MA equal to B and MB equal to C. MA equal to B means M, which is ABCD, times A which is 1 comma minus 1, MA equal to minus 1 comma 2, minus 1 comma 2. Right, that's this equation, MA equal to B. Let's see what this reduces to. This reduces to A minus B equal to minus 1, right? A minus B equal to minus 1, and then C minus D equal to 2. So Let me call this equation 1. Let me call this equation 2. That's out of MA equal to B. Let me look at what MB equal to C gives. MB, M which is ABCD, B which is minus 1 comma 2, minus 1 comma 2, equal to MB equal to C, which is 1 comma 0. All right. Let me see what ABCD turn out to be from these equations. So now this is going to give me minus A plus 2B equal to 1. That's equation 3. And then minus C plus 2D equal to 0. That's equation 4. Let me solve 1, 2, 3, 4 and see what transpires. Okay. Now if I add 1 and 3, what do I get? I get B equal to 0. If I add 1 and 3, equation 1 and 3, A will get cancelled with A. 2B minus B is B. So B turns out to be 0. B is 0. Now when B is 0, A is very clearly minus 1. A is minus 1, as you can see. And if A is minus 1, now let me use these two equations to solve for C and D. Equation 2 and equation 4. So when I add 2 and 4, I get D equal to 2. I get D equal to 2. And if D is 2, C turns out to be 4, as you can see. C turns out to be 4. So I know ABCD. So I know the matrix M. I know the matrix M. The matrix M is A, B, C, D. That's the matrix M. Right? M minus Xi. So M minus Xi is going to be minus 1 minus X, 0, 4, 2 minus X. That's M minus Xi. And what's determinant of M minus Xi? Determinant of M minus Xi, as you can see, is minus of 1 plus X, minus of 1 plus X into 2 minus X equal to 0, giving you X equal to minus 1 and X equal to 2. So very clearly, I know X1 and X2. X1 is the larger one, so X1 must be 2, the larger of the two roots, and X2 is the smaller root, which must be minus 1. Right? So, and I want to be able to find the value of 5x1 plus 2x2. So 5x1, 5 into 2 plus 2x2, 2 into minus 1. So 10 minus 2, that makes it 8. 10 minus 2, that's the value of this. Right? 5x1, 10 minus 2, 8. Right? So fairly simple problem. Pretty much within the reach of everyone. Just that, you shouldn't have made computational errors while solving these equations. But nothing difficult about it. Let's move on to the next problem. Bye-bye. So the next problem is about this matrix. Cos alpha, sin alpha, minus sin alpha, cos alpha, right? And there is another matrix B defined in terms of A. B is given to be A plus 4A squared plus 6A cubed plus this. And it's given that determinant B is 1. Now if such be the case, how many values of alpha exist in the interval minus 2 pi to 2 pi for which these two conditions would be met? That's the problem. Right away when you look at the problem, does it ring a bell? This expression, does it remind you of anything? Yeah. So obviously it's not supposed to be complicated, right? It's not supposed to be complicated. What you get here is, you could take A common from all of these, A, and then you have like a power 4, and this is 4C1. Realize that? 4C1 A cubed, right? Plus, this is 4C2 A squared, this is 4C1 A, and this is I. This is I, isn't it? This is I. And you know what you could have done is, when you had a to power 4, this you could have said is I to power 1. This you could have written as I square, right? To make binomial sense, sense. And then this as I cubed. And this is I, which is the same as I to power 4. Yes or no? Do you realize this? Which means now this is going to be rendered as A plus I whole to power 4. I is an identity matrix. Yes or no? So that's B. That's B. And determinant B would be determinant A into determinant of A plus I whole to power 4. And that's given to be 1. That's given to be 1, determinant B. What's determinant A? Cos square alpha plus sin square alpha. That's 1. Determinant A is 1. So that brings us to determinant of A plus I whole to power 4 equal to 1. Yes or no? Now, what is A plus I? A plus, the identity matrix, is going to be 1 plus cos alpha sin alpha, right? 1 gets added to the diagonal elements, that's all, minus sin alpha and 1 plus cos alpha, right? Yes or no? And what would determinant of A plus I be? Determinant of A plus I would be 1 plus cos alpha whole squared plus sin square alpha. Yes or no? So that makes it cos square plus sin square, so that makes it 2 into 1 plus cos alpha. Yes or no? Now realize that this number can never be negative, because cos alpha plus 1 is always greater than or equal to 0. So this can never be negative. That means determinant of A plus I must be plus 1 only, can't be minus 1. Could have been plus 1, right? This gives me determinant of A plus I is plus 1 or minus 1, right? The real values. It couldn't have been minus 1 because determinant of A plus I is this, which is never negative. Do you understand what I'm saying? So this equal to minus 1, determinant of A plus I equal to minus 1 is ruled out. Got me? So this must be equal to plus 1. Yes or no? So this gives me 2 cos alpha is minus 1, cos alpha is minus half. Cos alpha is minus half. Realize how many values of alpha exist in the interval minus 2 pi to 2 pi? 4, very good, exactly. Because see, minus half cos alpha will assume a negative value in this quadrant and this quadrant, right? So when I traverse minus 2 pi, this is minus 2 pi, and I keep going this way, I will encounter these lines 4 times. 4 times. Yes or no? In minus 2 pi to 2 pi, I am going to encounter these two radial lines 4 times. So cos alpha equal to minus half in the interval minus 2 pi to 2 pi will have 4 values of alpha. 4 values of alpha. Yes or no? 4 values of alpha in this interval. Clear? Stand by. P given and a diagonal matrix N whose elements are N1, N2, N3, N1 less than N2 less than N3. And what are N1, N2, N3? They are the roots of this characteristic equation, right? So obviously if I solve this equation, I will get N1, N2 and N3. So what's P minus Ni? P minus Ni is 1 minus N, 2, 0, 2, 1 minus N, 0, 0, 0, 1 minus N. This determinant equal to 0. Very clearly it will be a cubic Nn. And we'll get three values of n. One would be n1, the other one would be n2, n3, right? Let's see what this turns out to be. This gives me 1 minus n whole cubed minus 2 into 1 minus n equal to 0, right? And I could jolly well take 1 minus n common from this, just to simplify calculations. 1 minus n, so that gives me 1 minus n whole squared minus 4 equal to 0. That produces 1 minus n. This is 1 minus n plus 2, that is 3 minus n. 1 minus n minus 2, which is minus n minus 1 equal to 0. So that gives me three values of n. The smallest will be n1, so minus 1. n1 is minus 1, n2 is 1, and n3 is 3. So I know n1, n2, n3. So I know the diagonal matrix n1, n2, n3. So if it's a diagonal matrix, what would be the determinant of n? If it's a diagonal matrix, what would be its n1, n2, n3? Precisely, that's going to be product of the diagonal elements for a diagonal matrix. So that makes it minus 3. That makes it minus 3. Now, determinant of adjoint n would be determinant of n whole squared, right? It's a 3 by 3 matrix. So 3 minus 1. Yes or no? Right? So determinant of n whole squared, that makes it 9. Right? Look at this. Q transpose is Q plus alpha I. I want to be able to find the value of alpha. Alpha is a scalar. Alpha is a scalar, a number. Let me take the transpose of both sides. Let me take the transpose of both sides. So this will be Q then. This will be Q transpose. And this will be alpha is a scalar. I transpose is I only. So alpha I is what I get if I took the transpose of both sides. Now if I add these two equations, then I get Q plus Q transpose equal to Q plus Q transpose plus 2 alpha I. So that gives me 2 alpha I equal to 0. Is 0 means null matrix. It's not 0, it's a null matrix. Q plus Q transpose, right? It's a null matrix, not 0. It's a null matrix, right? So if 2 alpha I is a null matrix, I is not a null matrix. Alpha, therefore, when it gets multiplied with I, causes it to become a null matrix. That means alpha must be 0. Alpha must be 0, right? This is a null matrix, but alpha must be 0. Understand, this is a matrix, but this is the number 0. Alpha is 0. 2 alpha I is a null matrix. Got me? Confusion? This, you understood? This. So if I took the transpose of both sides, so Q transpose will be Q. I'm taking the, if this is equal to this, then the transpose of this will be equal to transpose of this. Q transpose is Q. This will become Q transpose. Alpha I transpose is alpha I only, because I when transpose will give me I only. So that's going to give me alpha I. Now when I add these two, Q plus Q transpose is Q plus Q transpose plus 2 alpha I. So that gives me 2 alpha I is a null matrix. So alpha must be 0. This is a null matrix, but this is the number 0. Right? So now, so we get alpha equal to 0. Alpha equal to 0. Right? Now let's look at the third part number 7. Right? Trace of P to power 2012. Trace of P to power 2012. Right? So in these cases, you know, you have to, yes, the only way you can handle this is to observe a pattern. Precisely the case. So let's find P squared, P cubed, etc. and generalize the pattern. Can I remove the clutter from here? Right? Precisely, the pattern is what you, if P is this, so let me first find P squared. So P is 1 2 0 2 1 0 0 0 1, right? P squared 1 plus 4 5 plus 0 5, then 2 plus 2 4 plus 0 4, and then 0 0 and then 0, right? 0, right? The next one 2 plus 2 4 plus 0 4, and then 4 plus 1 5, right, and then next one 0 0 and then 0. Okay, then the third one 0 0 0 0 0 0 and 0 0 0 and 0, right, right, and then this one 0 0 1, right, that's p squared, that's p squared. Trace of p squared would be 11. Trace of p squared is 11. Anyways, let me find p cubed. P cubed is p squared into p. P squared is 540 450 001 into p, which is 120 210 001, right, that's p cube. Let's first find p cube. 5 plus 8 13, okay. Then 10 and 4 14 and 0, and then 0 0 0, right, okay. Then this 4 plus 10 14, and then we have 8 plus 5 13, and then 0, right. Then this 0 0 0, right, then 0 0 and 0 0, okay, and then this 0 0 0, and then this 0 0 1, right, that's p squared, p cubed, that's p cubed. Okay, let's see what this is. Trace of p squared, trace of p squared is 11, and trace of p cubed is 27. Now this is like 3 cubed and this is like 3 squared. Now I guess perhaps you might want to check, you will perhaps find, so this is like 3 squared plus 2, this is 3 squared plus 2, right. Likely that you'll find trace of p power 4, this is 3 squared plus 2, this is 3 cube, you'll find 3 to the power 4 plus 2. Likely that you'll find trace of p to the power 5, you might want to check that out, but I'm guessing this would be 3 to the power 5, right. So every time the powers are even, then 3 to the power, that power plus 2. So p to the power 2012 will belong to this sequence, p squared, p to the power 4, p power 6, that sequence. So I'm guessing p to the power 2012 would be 3 to the power 2012 plus 2. You might want to just check with p power 4 and see if this is happening, then you just go ahead and generalize that. This is what you need to be. So you need to just multiply a few matrices very fast and arrive at a pattern. That's what you need to do, right? Stand by. Next problem is about two square matrices, idempotent. And AB plus BA and AB minus BA are null matrices. That's given, right? We want to find all possible values of the determinant of A minus B. That's what we need to be able to do, right? Now, if A and B are square idempotent matrices, that means A must be equal to A squared, and B must be equal to B squared. That means A squared minus B squared must be A minus B, subtracting. Yes or no? Now, if I say this, A square minus B square, is this right or wrong? Is this right or wrong? Can I do this factorization in this case? They commute, because realize that A squared minus B square, all right, A minus AB and plus BA, that's a null matrix. See, minus AB plus BA will be a null matrix. Yes or no? That's why. Because AB is equal to BA in this case, right? Because AB minus BA is a null matrix, so AB is equal to BA. They commute. So the minus AB will cancel with a BA. BA will get cancelled with minus AB because of this condition, right? That's why I could write A square minus B square as A plus B into A minus B, right? Now, let me take the determinant of both sides. Let me take the determinant of both sides. So that gives me determinant of A plus B into determinant of A minus B minus determinant of A minus B equal to 0. Now they are all scalars, so I can take determinant of A minus B into determinant of A plus B minus 1 as 0, right? It gives me two possibilities. One, determinant of A minus B is 0, is one possibility, or determinant of A plus B is 1, right? Now, so for sure one possibility is determinant of A minus B is 0. But if determinant of A plus B is 1, then what's the value of determinant A minus B? We need to find out. That means there are more possibilities, right? This gives me determinant of A minus B as 0. But if this is 1, then what's the value of determinant A minus B? Right? Okay. So now we have determinant of A plus B as 1. Realize A minus B whole square would be A squared plus B squared. Why? Because minus AB and plus BA will get cancelled, because AB minus BA is a null matrix. I'm sorry, A minus B whole square is like A minus B into A minus B, so which is like A squared minus AB minus BA plus B squared, right? Don't tinker with the order. Now this is like minus of AB plus BA, isn't it? But AB plus BA is also a null matrix. That's why this turns out to be A square plus B squared. Yes or no? Because AB plus BA is a null matrix. Good. So this then, right? But A square is A. It's a idempotent matrix. B square is B. So which means A minus B whole square is A plus B. Now take determinant of both sides. Determinant of A minus B whole square is determinant of A plus B, which is 1. I'm exploring this case now, right? Determinant of A plus B is 1. So then this is 1, and determinant of A minus B whole squared is determinant of A minus B whole squared, right? It's a property. It's a property. So that gives me determinant of A minus B as plus minus 1. So determinant of A minus B could be 0, could be plus 1, could be minus 1. There are 3 possibilities then, right? Yes or no? Stand by. Satisfying this condition. A transpose is this, B transpose, C transpose, D transpose. We need to authenticate these two statements. Statement 1 is S cubed equal to S, whether or not it's true. And S squared is S power 4, whether or not it's true. We need to check those, right? So, what is S? S is given to be ABCD, right? S is given to be ABCD. S is given to be ABCD. Right? Yeah. If this will be if this is true, then this will also be true. Yes. Right? Now not AA inverse I. If AA transpose is I, A is called an orthogonal matrix. For orthogonal matrices, that will hold good. Now, what is S cubed? S cubed is S, which is ABCD, into ABCD, into ABCD. Right? Clear? Yes or no? S into S into S, S into S into S, that's S cubed. Clear? Now, what is ABC? ABC is D transpose. right? ABCs. What is DAB? DAB is C transpose. What is CDA? CDA is B transpose. What is BCD? BCD is A transpose, right? Yes or no? Now realize that this then is like D transpose, C transpose, B transpose, A transpose, right? This is like BCD transpose into A transpose, property of transpose, right? But what is BCD? BCD is A transpose. A transpose transpose will be A. So A transpose. Yes or no? And A transpose is what? A is A and A transpose is BCD. So that's S. That's S. So S cube turns out to be equal to S. So if S cube turns out to be equal to S, then multiply by S both sides. So you get S power 4 is S squared. Right? Stand by. The next situation is about a 3 by 3 matrix Aij, right? A11, A12, A13, and so on and so forth, right? And what's given is A plus A transpose. A plus A transpose is given, which is this matrix. And it's given that this is a symmetric matrix. A plus A transpose is symmetric. Also, these three elements of A are positive roots of this equation, We want to find determinant A. We want to be able to find determinant A. Right? Okay. First of all, tell me, what is the sum of these roots? A12 plus A23 plus A31. What's the sum of these roots? 6. 6 minus of minus 6. 6. That means the arithmetic mean is 2. The arithmetic mean of the roots is 2. Yes or no? Right? The geometric mean of these roots, is going to be cube root of the product of the roots is minus 1 cubed into minus 8. That means 8. That means 2. Cube root of 8. That's 2. That means AM turns out to be GM and these numbers are positive. That means all quantities must be equal because AM equal to GM. That means A12 must be equal to A23 must be equal to A31. Each will be equal to 2. Each will be equal to 2. Now, this is known to be a symmetric matrix. That means this must be equal to 4. A21 plus A12 must be equal to 4. And we found that A12 is 2. So A21 must be 2. A21 must be 2. Right? Similarly, this will be equal to 4. And it's given, what we have figured out is A31 is 2. So A13 will also be 2. Because this is equal to 4 and one of them, A31 is 2. Right? Similarly, 4 must be equal to this. A23 plus A32. Right? And A23 is 2. So A32 must also be 2. Right? Yes or no? Now, when I add A to A transpose, A and A transpose have the same diagonal elements. Yes or no? A and A transpose will have the same diagonal elements. Right? That means when I add A to A transpose, the diagonal elements get added, get doubled. Get doubled. That means 2A11. 2A11 must be 6. So A11 must be 3. Right. A11 must be 3. A22 must be 5. And A33 must be 4. Do you all realize what I did here? So, what is the matrix A? The diagonal elements are 3, 5 and 4 and everything else is 2. Everything else is 2. What's this determinant? 3 into 20 minus 4, 16 minus 2 into 8 minus 4, 4 plus 2 into 4 minus 10 minus 6, 48 minus 12 minus 12 minus 48 minus 24. 24, is it? Does it turn out to be 24? 48, 1 minute, let me just check. 3 into 20 minus 4, 16 minus 2 into 8 minus 4, 4 and plus 2 into 4 minus 10 minus 6. So minus 8 minus 12 minus 14. Right, 28. This is minus 8 minus 12 minus 20, 48 minus 20, that is 28. Right, stand by. Next problem is a matrix A, a diagonal matrix D1, D2, D3, D4, and DIs are all greater than 0, that's given. And it's also given that even though D1, D2, D3, D4 could all be varied, but they must subscribe to this condition. D1 plus 2D2 plus 4D3 plus 8D4 must always add up to 16. Such must be your choice of D1, D2, D3, D4. Within this, you can vary D1, D2, D3, D4 as long as you maintain them positive. Now we have a function which is logarithm of the determinant of A. Obviously, determinant of A is a variable number because D1, D2, D3, everything can be varied, right? To the base tan x plus cot x, where x must belong to 0 to pi by 2, right? We want to maximize fx. We want to find the maximum possible value of fx. Very clearly, what is fx? Fx is log of determinant of A divided by log of tan x plus cot x, right? So if you want to maximize this, then maximize this and minimize this. Minimize this means minimize tan x plus cot x. Minimize tan x plus cot x. In this case, maximize determinant A and minimize tan x plus cot x. That's what you want to do. That means, and what's determinant A by the way? D1, D2, D3, D4? Now, any idea? Absolutely, absolutely. What we'll do is AM greater than GM. Very clearly, fourth root of D1 into 2D2 into 4D3 into 8D4. That's the geometric mean of these numbers, D1, 2D2, 4D3, these four numbers, and that must always be less than or equal to the arithmetic mean. What's the arithmetic mean of these numbers? 16 by 4. 16 by 4, that is 4. 4 is the arithmetic mean of these numbers, yes or no? Right? Very clearly then, I raise both sides to power 4, right? I raise both sides to power 4. So this will be like 4 to power 4, 16, 256, right? And what is this? 8, 8, 64, 256, so 4. So I get D1, D2, D3, D4 less than or equal to 4, right? That means maximum value of D1, D2, D3, D4 is 4. That's the maximum value of D1, D2, D3, D3. And what's the minimum value of tan x plus cot x? What's the minimum value of tan x plus cot x? 2, because see, tan x plus cot x by 2 is greater than or equal to square root of tan x cot x. Yes or no? AM greater than GM, x is in the first quadrant. So tan x plus cot x greater than or equal to 2. That means minimum value of tan x plus cot x is 2. Yes or no? Is 2. So then fx maximum is going to be log of determinant A. I have to maximize determinant A. Maximum value is 4. So log 4 to the base log 2, which is very clearly 2. Right? This is 2 squared, so 2 log 2. Log 2 will get cancelled, so 2. Right? So maximum value of fx is 2. Right, so we have a matrix A, L, M, N, P, Q, R, 1, 1, 1, and B is square of A. B is square of A. All right. And this is a relationship connecting L, M, P, Q, etc. These are 3 relationships. Right? And we want to be able to find the determinant of B. We want to be able to find the determinant of B. I'll ask you one very simple question. Suppose I have this determinant L, M, N, a determinant, not a matrix, just a determinant P, Q, R, 1, 1, 1. Have you encountered this expression, half of this? Half the area of a triangle, or its magnitude, because this could also turn out to be a negative number, right? Which means, what kind of a triangle will it represent? Area of what kind of a triangle? Vertex L and P, A, vertex B, M and Q, vertex C, N and R, right? Half of the determinant of A and magnitude of that will represent the area of this triangle. Yes or no? Because, see, again, this number could turn out to be a negative number. So, magnitude of this. So, what would this be? This would be plus minus area of triangle ABC. Yes or no? This can be plus minus, this determinant can be plus minus area of triangle ABC. Do you all understand this? Now, what is this? AB. Distance between LP and MQ. LP and MQ. So this must be 3. MQ and NR. MQ and NR. This must be 4. And this must be 5. This must therefore be a triangle essentially like this. A, B, C, 3, 4, 5. Yes or no? And area of this triangle is what? 6 square units? Is 6 square units? That means this determinant must be plus minus 6. Yes or no? That means this determinant of A, this is determinant of A, this is determinant of the matrix A, can be plus minus 12. Can be plus minus 12, right? Now go back to this. Determinant of B would be determinant of A whole squared, but determinant of A can be plus or minus 12, so that makes it a 144. That makes it 144. Yes or no? Right? Stand by. Next problem, these 4 statements, we need to check if they are true or not. Okay. So the first part A is ABC. AB are square matrices of order 3. A is non-singular. Non-singular means determinant is not 0. And if AB is a null matrix, B is null. Is it true or false? If AB is a null matrix, then B must be a null matrix. False. Let's see. Okay. AB is a null matrix, right? Now, if A is non-singular, that means A inverse must exist. That means A inverse exists, right? That means A inverse exists, right? Let me do multiply with A inverse. B must be A inverse into a null matrix, which will be a null matrix. But A inverse A is I, identity matrix. I into B is a null matrix. But I into B is B. I into B is B. which means B indeed must be a null matrix. So true. কোনটা? Huh? No, but determinant B is 0 doesn't mean that B is a null matrix. See, a determinant of a matrix could be 0, but it may not be a null matrix. It's not all its elements need to be 0. Right. Right? Right? Let me look at option B. A, B, C are square matrices of order 2. Determinant A is known, determinant B is known, determinant C is known. We need to check if this is true or not. Now, ABC is what? It's going to be a square matrix of order 2 because ABC are all square matrices of order 2. So, ABC is going to be a square matrix of order 2. So, 3 gets multiplied with every element, right? So, this will be 3 to power 3 to power n. N is what? 2? 3 to power 2. 3 to power 2. Right, right. So this 3 can come out. So that's 3 squared. 3 to power n. Right? 3 to power n. N is the order of the matrix into determinant A, which is 2, into determinant B, which is 3, into determinant C, which is 4. 24 into 9, 180 plus 36, 216. Okay, true. Option C. So this is true, this is true. A is a square matrix of order 3. Determinant A is half. Does it mean adjoint A inverse is 8? What is determinant of adjoint A inverse? Would be determinant of A inverse to power 2? Determinant of A inverse to power 2, which is 1 by determinant A whole squared, which is 4, because determinant A is half. So this is not true. Every skew symmetric matrix is singular. Is it true? Every skew symmetric matrix of an odd order will be singular. Every skew symmetric matrix of an odd order will be singular. Huh? No. Skew symmetric, it's skew symmetric given. See, I can have a skew symmetric matrix, for example, of an even order, which could be, say, 1, 2, 4, minus 4, right? It's a skew symmetric matrix of an even order, but is its determinant 0? No. Important thing is every skew symmetric matrix of an odd order will be 0. Every skew symmetric matrix of an even order may or may not be 0. So this is not necessarily true. This is not true. Not every skew symmetric matrix is singular. There could be skew symmetric matrices of an even order which are non-singular. Non-singular. This is non-singular. Got me? So problem 14 is about 3 square matrices of order 3, ABC, satisfying A squared plus 2I equal to 0, and determinant of 2C minus A squared is 32, and this equal to 0. We want to be able to find the value of determinant of B minus A whole square, right? So determinant of 2C minus A squared equal to 32. This minus A squared can be written as 2I. So this is like twice C plus I equal to 32. Now C plus I is going to be a determinant, is going to be a matrix of order 3. So if 2 comes out, that's going to bring about 2 cubed. 2 cubed, it will become 2 cubed. And therefore determinant of C plus I is 4. Right? Determinant of C plus I is 4. Right? Now, let's look at this. Realize that 8 to power 5 is what? A squared whole squared into A. What is A squared? A squared is minus 2I. into a. So I square would be I, and I into a would be a. So this simply becomes 4a. So a to power 5 would be 4a. A cubed would be a squared into a, where a squared is minus 2i into a, right? So which is minus 2a. So this will become plus 2a, 2ac plus 2ac. A squared again I write as minus 2i. So this will become minus 2b minus 2bc equal to 0. Now I could take 2a common. So that's like a I plus c, 2i plus c minus 2b into I plus c, nothing is coming common. Oh, okay. I plus c is not coming common. So 2a cubed, a square is so this will become 4a. See, this is 2a cubed. A cubed is minus 2a, so this will become plus 4a. So this is 4 I take common, 4a into I plus c minus 2b into I plus c, right? That's equal to 0. So that gives me like a 4a minus 2b into I plus c equal to 0. What would have been wrong? Can you tell me? If I had written I plus c into 4a minus 2b equal to a null matrix, that would have been 0. It's not 0, by the way, it's a null matrix. So don't call it 0, it's a null matrix. So if I had written like I plus c, if I had taken common and I would have said 4a minus 2b, this would have been wrong. Why? Because see, this gives me minus 2cb, but I have 2bc. Do you realize that in that multiplication? Minus 2bc, but if I write like this, I'll get minus 2cb, which would be wrong. You must take cognizance of the same. You know what I'm saying? So if I had written this as I plus c into 4a minus 2b, that would have been wrong, right? Now, determinant of c plus I or determinant of I plus c is given to be 4. That means c plus I is a non-singular matrix. C plus I is a non-singular matrix. So what I could do is, I could do a 4a minus 2b into I plus c into I plus c inverse exists then. That must be O into I plus c inverse, which would be null matrix. This exists because I plus c is non-singular. Its determinant is 4, right? And this will be I, right? And this therefore will be 4a minus 2b. 4a minus 2b is a null matrix. So B must be equal to 2a. B must be equal to 2a, yes or no? So this determinant B I write as 2a minus a, which is mod a whole square. Mod a whole square. What is a? Mod a whole squared is like mod of a squared. Mod of a squared, right? This can come out. What is a squared? A squared is minus 2i. Mod of minus 2i. I is a determinant of order 3. So 3. So this will become minus 2 cubed. This will become minus 2 cubed. Yes or no? This will become minus 2 cubed. So minus 2 cubed into determinant of I. Determinant of I is 1. So that makes it a minus 8. That makes it a minus 8. Stand by. Abar bolo. Are natural numbers, right? And it's given that determinant of adjoint A is this, right? How many such matrices exist? Given that x, y, z are natural numbers, how many such matrices exist? Now first of all, this determinant is going to be determinant of A to power n minus 1 whole square, where n is 3. N is 3. That's 2 to power 8, 3 to power 4. N is 3, so determinant of A to power 4 is 2 to power 8, 3 to power 4. Determinant A is 2 squared into 3, 4 into 3 plus minus 12. These are two possible values of determinant A, right? Plus minus 12. Now from that, determinant A is x into 4 minus 3 1 minus y into 2 minus 3 minus 1 minus z into 1 minus 2 minus 1. That's the determinant. So which is like x plus y plus z. Very clearly x, y, z are natural numbers. So determinant A can't be negative. So we'll ignore minus 12. It must therefore be 12. And I need number of natural number solutions to this equation. That will give me the number. So the number of natural number solutions to this equation, as you know, is 11C2. How much does it turn out to be? 55. 55 would be the number of natural number solutions to this equation. N minus 1 C R minus 1. A is this, P is this, and Q is defined in terms of P and A, P transpose AP. P transpose obviously is this, and as you would have checked, PP transpose is I. If you multiply these two matrices, you will get an identity matrix. We need to find the value of P, Q to power 214, P to power P transpose. So this is P, Q to power 214, 2014 is P transpose AP into P transpose AP into P transpose AP. How many times? 2014 times. 2014 times, right? This happens 2014 times. 14 times, right? Now, look, this PP transpose would be I. This PP transpose would be I. This PP transpose would be I. This PP transpose, this PP transpose, that'll all be I, right? We'll be just left with 2014 A's. So this is going to give me A to power 2014, right? Yes or no? Essentially, then the problem boils down to finding A to power 2014. Now you'll have to work through patterns. Find A squared, etc. Let's do that, right? A is this. So A squared would be what? 1201. 1201. That's A squared, right? Let's see how much this turns out to be. 1 and then 2 plus 1 3 and then this 0 plus 0 0, then this 0 plus 1 1, right? That's A squared, is it? 1041, right? Right? 1041. What is A cubed? A squared, which is 1401 into A, which is 1201, right? That's A cubed. Let's see how much this turns out to be. 1, then we'll have 2 plus 4 6 and then 0 and then 1, right? That's A cubed. Let's look at A to power 4, which is A cubed into A. A cubed is 1601 into A. A is how much? 1201, right? How much is it? This 106 into 8 and then 101, right? Okay, so what happens is, see, when you had A squared, this all other elements will remain the same, 101, but this becomes twice this. This is 2 into 3. 4, this is 2 into 4. So you would expect A to power 2014 as this matrix. 1 4028 01 is what you would expect as A to power 2014, and therefore the value of this. Clear? Stand by. The last member of this revision sheet on matrices. Again, last doesn't mean it's difficult. Again, a very simple problem, as were the previous problems. We have set of natural numbers fragmented into matrices. A matrix with the number 1, a 2 by 2 matrix, call it A2, 2, 3, 4, 5, a 3 by 3 matrix, call it this, 3 by 3, and there is an A10. A1, obviously this A10 is going to be a 10 by 10 matrix, which should have diagonal elements A1, A2, A10. Now what is it that we want to find out in this problem? We want to find the trace of A10. That means not the trace of A10. We want to find the units digit of the trace of A10, which is like A1 plus A2 plus A10. They add up to a certain number, and when they add up to a certain number, this number has a units digit. We only want to find the units digit of A1 to A10. A1 plus A2 plus A10. Now, would you not want to believe that these numbers A1, see, there are 10 members here, right? So there are 10 members in all. So after A1, there are 9 members in the first row, right? So what really happens is there is increase by 1 unit when you go from one member to another, 9 units. So by the time you reach this last position, you get like a A1 plus 9, right? And when you come down here, you get like a A1 plus 10. And then A2 therefore must be A1 plus 11. A2 must therefore be A1 plus 11, right? Similarly, A3, A2 must be A1 plus 11. A3, similarly, you know, A1 plus 11, then another 11 units you will have to add up to get to A3. So A3 would be A1 plus 2 into 11. A4 would be A1 plus 3 into 11. And A10 would be A1 plus 9 into 11. Right? Now, if I add A1 to A10, which will give me the trace. So if I add A1 to A10, that means summation AR, R equal to 1 to 10. What do I get? Hey, A1 appears 10 times, so that is 10 A1. Plus, there is 11 featuring here as a common, and then I have like a 1 plus 2 plus 3 up to 9, which is sum of the first 9 natural numbers, 9 into 10 by 2. That is what you get, right? So which is like 10 A1 plus, realize that this is 5, 45, 11 into 45, right? This number ends in 5. This number will end in 0. So this entire thing will end in 5. This ends in 5. This ends in 5. Therefore, the units digit of the trace of A10 is going to be 5. It's going to be 5. And you know, we don't have to find A1 to find the units digit of trace of A10, right? So that's the last number. Now what has really happened by the time you've finished these 10 problems? It's kind of putting you in a comfort zone with matrices. Some important properties, if not all, have been utilized towards solving problems on matrices in this first segment. Look forward to more such revision sessions on various topics. I'll try and do justice without taking recourse to black magic. Have fun until then and stay out of trouble. All the best for your mains and all the best for all that is to come. Take care.